Greetings and welcome back. I'm going to refer to this particular vignette as every distribution has its moments. And the reason for this is that we've made a lot of noise about the fact that distributions provide a window and a mechanism, that they tell us a lot more than just the means, that there's signal in the noise. There's all these slogans that we've kind of unleashed to make this point about the virtue of using the entirety of the distribution. And I wanted to say that that there's a little bit more we can say about a distribution at the level of individual numbers. And so, if I were to call up my mom and I wanted to describe to her a distribution, the first two things that I would want to tell her are something about the mean, and then I would want to tell her about how wide the distribution was. You could think about this. This is something that goes back all the way to our grade mongering days, in school, when people are worried about, how many people got A's, how many people got B's, what was the average score on the exam, and all that kind of nonsense. So that's a very intuitive, everyday example that I think everybody can appreciate. And that's a very interesting thing that we can reflect on in light of our most recent election in the U.S. So I'm recording this in January of 2021, which means that in November, roughly 3 months ago, we had an election, which was a competition between Donald Trump and Joseph Biden. And for me, if I were to try to characterize the most interesting thing about U.S. elections, presidential elections, in some ways, the most confusing thing of all. And, it's really a matter of indifference whether you're talking about this election or another one. So roughly speaking, half the people vote for each candidate, and so that's a statement about distributions, It's a statement about the width, if you like, and so on. So at any rate, what I want to do here, so the logic of this little vignette is I want to define averages and moments. So that's the first thing. And then I want to give the example of a rectangular distribution. This is in some ways the simplest of all probability distributions. And what I would say to you actually is, if you're on that desert island with Wilson and you want to think about a probability problem, the first thing to do is not to use a Gaussian, in my view. The first thing to do is to use a rectangular distribution, because you can do all the integrals analytically, basically without doing integrals, just by multiplying things and computing areas and stuff like that. Then I will talk about the example of the Gaussian distribution. And then I will probably say something about the Poisson distribution. And then perhaps we'll have, as a homework, just a reflection on the binomial distribution and the exponential. So, homework, exponential, and binomial. And this all goes in the general category of the things that I think it's worth bearing in mind when you think about probability distributions writ large, but then also, I'm very interested, very, very interested, not for you, but for me, in what it means to master our craft and how does one attain mastery. And, I'm intrigued by sports analogies, and maybe those are foolish, I don't know, but I don't think they're foolish. I think they're actually right. And one of the things that I note and find very interesting, whether it's in professional football players or professional basketball players or runners, let me give you an example. There's a really great long-distance runner, American. I forgot his last name. He's from Oregon, tall, thin, blonde kid. I think maybe his name's Galen something. Anyway, there's a video of him you can find on YouTube where he won some 10,000 meter race, and then it says and then the video says 40 minutes later, and then what you see is him practicing 400 meter sprints. And it's getting late in the day, and by the time he's on his fourth one, it's dark. And he's out there with his coach and a light, and he's still running 400s. I think about Tony Gwynn, he's about my age, and unfortunately he left us probably a decade ago. He was one of the great hitters, one of the greatest hitters in the history of Major League Baseball, and he would take batting practice after games. Somebody like Kobe Bryant, Steph Curry, Magic Johnson, Larry Bird, they all would do many free throws every day. And I remember retirement questions to a professional football quarterback named Peyton Manning, and he said he would know it was time to retire when he didn't enjoy the practice part anymore. And I think all I'm really telling you, and maybe people listening to this will think I'm an idiot or think I'm naive or that I'm not a serious researcher or whatever. That's fine. I don't really care. For me, there's this great pleasure in what I'm about to do. This is me practicing the craft. And if you find it amusing or interesting, that's cool. If you don't, you can just turn this off. So at any rate, so I think it's if you want to practice these things, just the starting place is to practice with the rectangular distribution. So the first point I want to make is about averages. And so we consider a probability distribution, a continuous probability distribution. I'm going to work with continuous probabilities for the moment. Continuous probability distribution, P of x. And just for kicks, let me draw it. I don't know what it is. I'm just going to make something up. It's something, just like this. And so that's P of x. That tells me the probability of getting different x values. And first thing I will say is that mu 0, which is defined as x to the 0 power average, is equal to minus infinity to infinity of P of x dx, and that's equal to 1. So this thing is called the 0th moment. And I'm just pointing out that the distribution is normalized. Okay? So that's the first thing I want to say about it. And that's going to be the case with all of the distributions that I'm going to talk about. So, and this was a way for me to sneak in the idea of the moments. So every distribution has its moments. I've just shown you the 0th moment, but now let's talk about the average of some f of x. So at every value of x, there's something which I'm going to call f of x, and the average of f of x is gotten by taking minus infinity to infinity, f of x, p of x, dx. This is the definition of the average of f of x. So this symbol means, for my purposes, average of. I've probably already said this in the course. I don't know. I don't remember. As you can see by looking at the list of vignettes at this point, we're 4 or 5 weeks in. There's more than 50 vignettes, and I wake up and think about, I wonder if I talked about this or that thing yet. And so this is going to be, a second spin on the question of averages. I know we've already calculated some averages, but I'm coming at it from a different angle this time. So the idea, if you like, is that I'm approximately, what I'm doing is that I'm going along. Now I'm going to discretize this thing. Let's say I break it up into a bunch of increments, and what I do is I find the value at xn, and then I multiply by the probability that I will have an x at values between xn and xn plus delta x. So that's what the average is. So given those ideas, now the definition of the moments. So in general, the nth moment is defined as minus infinity to infinity. And now I'm just going to follow the rule of what I just said about finding the average of a thing. So I have x to the n, p of x, dx. So that's what I mean by the nth moment. So let's consider some examples. So the first moment, which is x, that's equal to minus infinity to infinity of x, p of x, dx. That's mu1, and that's the average value. So that's what the first moment is. The first moment is the average of the distribution. It tells me, where if I have this wide distribution, it tells me if I, again, going back to calling my mom, this is the first thing I'm going to tell her. I'm going to say, I gave this test, and people on the average score is around 80% or something. I don't know. It's a terrible example because I would never talk to my mom about the average score on a test. First of all, I don't give tests because life is a test, and you're supposed to be your own most serious critic. But also, it's a stupid topic, the subject of grades. I'm not excited to talk about that. So, maybe a much more interesting thing would be to talk about the average velocity of the molecules in this room. That's interesting. That's a really wild thing. And if you want to do a calculation, here's an assertion. If I take the average energy of the molecules in this room, and I take a liter of that gas, there's enough kinetic energy in that all of those molecules to lift a bowling ball to the ceiling. That's something I learned from a really cool article by Chris Jarzynski that was in Physics Today. So the second moment, x squared average, that's minus infinity to infinity, x squared p of x dx. And let me note that often we're interested in a slightly different version of this, which is x minus x average whole quantity squared. So what's the point of that? This thing is really cool because what it's doing is it's the natural variable of the problem. Why do I say that? Because it's telling us about the dispersion around the mean. The problem with this quantity is that it's not smart enough to pick off which part of the x is due to the fact that the average is somewhere over here, and which part has to do with the width. And so somehow we want to actually be able to characterize the nature of the width. This thing, what it does, is it says, well, find out how far each point is from the average, and average over that thing squared. The reason for the square is that if I didn't square it, then for every one that's above the average, I'd have one that's below, and I'd end up getting 0. Okay, so let's expand this out. So this ends up being average of x squared minus 2x average x, and then plus average x quantity squared, and all of that is averaged. Now by the linearity, that ends up being, I'm being very pedantic in my notation, and I'm not doing this out of sloppiness. I'm doing it out of being pedantic. So let's look at this last term first, this thing. Average x squared is a number. So this thing, this first set of brackets gives us a number. Then if I take the average of a number, I just get the number back. So this last piece is nothing more. Oops. Of course, it would have helped if I'd written it correctly. It's equal to this. It's equal to nothing more than that. And then this thing, this middle piece, gives me average x times average x, which is equal to average x squared. And so the net result is x squared minus average x quantity squared. So that's how I would actually characterize the sort of natural width of the distribution. Okay, I can keep on going down this path. X cubed is the integral minus infinity to infinity of x cubed p of x dx. And this thing is a measure of the asymmetry of the distribution. So for example, if I have a Gaussian, it will be 0. All the odd moments will be 0 for a Gaussian. And all the even moments will be a function of the second moment. In other words, the second moment is all there is for the Gaussian. Okay, so that's basically my introduction to the notion of moments. So in terms of the framing of what we've done, we've defined the averages and moments. So now what I want to do is I want to talk about the rectangular distribution. So let's call it a toy model, the rectangular distribution. And let me draw it, first of all. So this is x, here's p of x. Let's call this a, let's call this b, and let's call this mu or something. And then this is a rectangular distribution, and the height of this thing, the height is 1 over b minus a. The reason for that, let's just demonstrate that. Normalization. normalization is that I want to make sure that minus infinity to infinity of p of x dx is equal to 1. But actually, in our case, that means a to b of h times dx, where h is the height, has got to be equal to 1. And that's equal to h times b minus a. Thus, h is equal to 1 over b minus a, as I just claimed. So the height of this thing is given by 1 over the width of it. That's just to guarantee normalization. Let's find the average. So mu is equal to the integral from, actually from a to b of x 1 over b minus a dx. So that's equal to 1 over b minus a, and then times 1/2 x squared from b to a, which is equal to 1 over 2 b minus a. And then I have b squared minus a squared upstairs, and that's equal to, let's see, that's equal to b minus a, b plus a, over 2 b minus a, which is equal to b plus a over 2. Exactly what you would expect. Okay, so that's the first moment of this thing, and then the second moment is going to be equal to 1 over b minus a, and then integral from a to b of x squared 1 over, I've already got the 1 over b minus a, and then dx, which is 1 over b minus a, and then what do I want to do? I have 1/3 x cubed b to a, and that's equal to b cubed minus a cubed over 3 b minus a, and that's all fun and good. And let's see, I think I can, let's see, do I see any further comments I want to make about this? Well, you know, I'll leave it as an exercise to you to compute this quantity, which is a measure of the dispersion of this thing, or, you know, how wide it is. So let's see. So we've now done just a quick reckoning of the rectangular distribution, and now I want to turn to the Gaussian. Okay, so that's example 2. And here we have p of x is equal to 1 over square root of 2 pi sigma squared e to the minus x minus mu squared over 2 sigma squared. So that's our representation of the Gaussian distribution with variance sigma, sigma squared, and with mean mu. And once again, we can evaluate the various moments. So mu 0 is defined as minus infinity to infinity of p of x dx, and that's equal to 1 over square root of 2 pi sigma squared, and then integral minus infinity to infinity of e to the minus x minus mu over 2 sigma squared dx. And I don't think I'm going to go through this here, although it's very fun. I'm just going to report to you, a crucial thing to know is the Gaussian integral. This Gaussian integral is one of those things that's worth memorizing. It's given by root pi over alpha, where you can see how I've defined alpha. And that's a fun integral to figure out how to do. I don't know how people were so clever as to figure out how to do this, but at any rate, you go into polar coordinates. I'm not gonna go into it right now. But all that I really want to point out is that using this, maybe I'll say thus, 1 over root 2 pi sigma squared, and then I have this integral let's choose u, choose u equals x minus mu, That implies that du is equal to dx, and the limits of integration are unchanged, so I have 1 over 2 pi sigma squared, and then minus infinity to infinity of e to the minus u squared over 2 sigma squared du, and by the scheme that I just told you, this is equal to square root of pi over 1 over 2 sigma squared, and thus the whole thing is equal to 1. So it's normalized. The first moment, as usual, is 1. Sorry, the 0th moment. So mu 0 equals 1. That's normalization. What about mu 1? Well, we already expect that we're going to get mu, but let's verify. So here I have 1 over 2 pi sigma squared, and then integral minus infinity to infinity of x e to the minus x minus mu quantity squared over 2 sigma squared dx. I'm going to do the same substitution again. So I say u is equal to x minus mu. That means that du is equal to dx. So I can rewrite this as 1 over square root of 2 pi sigma squared minus infinity to infinity. And then, well, this tells me that x is equal to u mu plus u. So I have mu plus u quantity squared e to the minus u squared over 2 sigma squared du. Okay, well, this is a little bit of a grind, not too much, but we've got to keep going. 1 over root 2 pi sigma squared, and then integral minus infinity to infinity of mu squared plus 2 mu u plus u squared e to the minus u squared over 2 sigma squared du. That's equal to 1 over root 2 pi sigma squared. Ooh, what did I do here? I don't know why I squared it. I got ahead of myself. I'm already doing the higher order moments. Sorry, please erase. Bear with me. Gotta redo. I got overly enthusiastic here. This is equal to 1 over root 2 pi sigma squared, and then minus infinity to infinity of mu plus u e to the minus u squared over 2 sigma squared du. And I want to point out that this one is 0. How do I know that? Just this term, okay? The reason it's 0 is because this part is what's called an odd function, and this part is what's called an even function. So if you like, maybe I can even try to draw this. Just in general, if you have, let me draw the Gaussian in green, and then let me draw the u in red. That's this thing. And then I'm not going to be able to do this very well, but their product is going to be something like this. So that's u e to the minus u squared over 2 sigma squared. This part is u, and this part is e to the minus u squared over 2 sigma squared. I left off the normalization. Okay, so the point is that this area here, because we're actually interested in the area under the curve, right, is going to cancel off this area over here. For every guy on the plus side, there's a corresponding one on the opposite side, and this is a more general result. If you take an even by an odd function, you integrate from minus something to plus something, the integral is going to be 0. So that's going to yield 0, and so once again, by the rules that we wrote down earlier, this is going to give us mu 2 pi sigma squared over root 2 pi sigma squared, which is equal to mu, as expected and as advertised. So in other words, the first moment of the Gaussian distribution is the mean. Okay, I'm just showing you that what I claimed is true. Now, finally, let's do mu2. So mu2, which is equal to average x squared, is equal to 1 over root 2 pi sigma squared minus infinity to infinity e to the minus x minus mu squared over 2 sigma squared times x squared dx. And okay, that's fine, a little bit of a hassle, but first let's do the surgery again, which is u is equal to x minus mu. That implies that du is equal to dx. And so I can rewrite my integral as 1 over root 2 pi sigma squared, and then integral minus infinity to infinity of u plus mu squared e to the minus u squared over 2 sigma squared du. And this is what I started to do last time. 1 over root 2 pi sigma squared, and then minus infinity to infinity of u squared plus 2u mu plus mu squared, and then e to the minus u squared over 2 sigma squared du. Gross. This guy is 0. It's 0 because of our rules that we just worked out. This guy is equal to u squared. Okay? The reason for that is it's just a number. So we have a number multiplied by our usual Gaussian integral, and we know that part's 1. So it's just mu squared. And the only piece that's left that we got to think about is this piece. So how am I going to do that? I'm going to use one of my sort of favorite tricks, which is that if I want this integral, minus infinity to infinity, of x squared e to the minus alpha x squared dx, I can always write that as minus d by d alpha of minus infinity to infinity of e to the minus alpha x squared dx. Why is that? Because if I take the alpha derivative of this thing, what does that do? It brings down a minus x squared out in front, which is exactly what we want. So this object I already know is root pi over alpha. And so the net result of this whole thing is root pi and then alpha to the minus 3/2. So in our case, what that leaves us with is, so what we have is that 1 over root 2 pi sigma squared minus infinity to infinity of u squared e to the minus u squared over 2 sigma squared du is going to be equal to the alpha in our case is 2 sigma squared, so it's gonna leave us with nothing more than sigma squared. How do I know that? Because I have sigma squared to the 3/2 over sigma squared to the 1/2. Wait, did I say that right? Yeah. And so the net result is that the second moment is given by sigma squared plus mu squared, and hence the dispersion x squared average minus average x squared is going to be sigma squared, as expected. Okay, so and if I were to, it's a good exercise for you to examine higher moments. So your exercise, do x cubed and x to the 4th for example, for the Gaussian. Okay, so in the scheme of what I wanted to do, I've now given you an impression of this for the Gaussian as well. And I think actually, rather than doing Poisson, I will leave that as an exercise. Well, I don't know. Maybe I'll just quickly say, since it's a discrete distribution, maybe I will just quickly illustrate. Oops. So the Poisson distribution. It's discrete, remember, and it tells us that P of n is equal to lambda to the n e to the minus lambda over n factorial, where lambda is the average of n. Okay, so normalization. So that's mu 0. That's given by n equals 0 to infinity of P of n, which is e to the minus lambda sum over n equals 0 to infinity of lambda to the n over n factorial. I'm hoping that you might remember that this is the series for e to the lambda, so this thing is equal to 1. So that's the first one. U1, that's equal to sum over n equals 0 to infinity of n P of n. That's given by sum n equals 0 to infinity of n e to the minus lambda, lambda to the n over n factorial, which is given by e to the minus lambda, and then sum n equals 0 to infinity of n, lambda to the n over n factorial. I took out the e to the minus lambda because it doesn't depend on n, so I can take it outside of the sum, and then I'm going to use my same rule, which is that this is e to the minus lambda, and then lambda times d by d lambda on sum n equals 0 to infinity of lambda to the n over n factorial. Take a look at what I'm saying. I'm saying that this lambda derivative, what will it do? It'll bring down an n. It'll leave behind a lambda to the n minus 1. This second lambda will come in and compensate for that and make it a lambda to the n again. So that's cool. And this thing is e to the lambda. And so what we get is e to the minus lambda, lambda, e to the lambda, which is just lambda. So as expected, mu1 is equal to lambda. The average of the Poisson distribution is lambda, as advertised. And then the last thing I guess we can do is we can compute mu2. Mu2 is equal to sum n equals 0 to infinity of n squared p of n, just being pedantic about it, which is n equals 0 to infinity of n squared e to the minus lambda, lambda to the n over n factorial, and this is equal to e to the minus lambda. And now I'm gonna just cut to the chase. I can use my same derivative rule again. Check it out. Let's verify that this actually makes some sense. So if I take the d by d lambda, what does it do? It brings down an n. This second lambda promotes it back to lambda to the n power. I take a derivative again. I bring down a second lambda. So now I have, I bring down a second n. So I have n squared, lambda to the n minus 1. But then this second lambda re-establishes this as lambda to the n power. And so this is exactly what we want. And so I need a little more room. So this is e to the minus lambda, lambda d by d lambda, lambda d by d lambda of e to the lambda, because that series is e to the lambda. That gives me e to the minus lambda, lambda d by d lambda, parentheses, lambda e to the lambda. And that's equal to e to the minus lambda, lambda, and then e to the lambda plus lambda e to the lambda, which leaves us with lambda plus lambda squared. We're almost done. So that tells me that average n squared minus average n quantity squared is equal to is equal to lambda squared plus lambda minus lambda squared, which is equal to lambda. And what that tells you is that the variance divided by the mean is equal to lambda over lambda, which is equal to 1. So that's kind of an interesting thing to bear in mind about the Poisson distribution. So what have we done? What was the whole point of this long explanation? I basically was interested in making sure to talk about averages and more generally about moments of distributions. The title of the vignette is every distribution has its moments, and I've shown you for the rectangular distribution, the Gaussian distribution, and the Poisson distribution what those moments are, and this should be a launching point for your own efforts to compute averages of things.